Okay. Yeah, so make sure that you're learning those proofs. I'm going to give you 2 of those. Basically, there's 5 proofs. So it's just like the first test. There's 5 proofs to learn. 4 of them will appear on the test, and you'll be asked to prove 2 of them. Okay. So you've got some time to work on that. Okay. Let's change gears a little bit. Talk about some other stuff. I want to make sure I'm covering kind of everything if I can, everything that I can think of. We've done a little bit with the Legendre symbol. Let's just let's take something a little simpler here. So, what number am I on?
4.
Number 4. Okay. Let's try to prove that phi of p to the k is equal to p to the k minus 2 times phi of p squared minus p. Okay, I don't think this is that exciting, but it doesn't have to be exciting, does it? Yeah, okay. So why would we ever be interested in calculating phi of p to the k? Exactly, that's the number of primitive roots of, in this case, p to the k, right? Okay, here's one thing I don't want anybody to do. Okay, everybody paying attention to me? Let's suppose I ask you how many primitive roots there are to the number 15. And so somebody does this, phi of 15, which is phi of, let's see, this is phi of 5 times phi of 3. It's multiplicative, right? That's one of your theorems you're learning. Phi of a prime is just prime minus 1, so this would be 4 times 2, which would be phi of 8, and this is a power of 2, so it's, I think that this is 2 cubed. Phi of 2 cubed would just be 2 cubed minus 2 squared, which would be 4. So are there 4 primitive roots of 15? No. How many primitive roots does 15 have? 0 is the right answer. This formula phi of n is the right formula if there are primitive roots for that number. But if the number doesn't have any primitive roots, then you don't want to be giving me this stuff. Okay, so actually, so I'm getting myself sidetracked from this problem, but that's okay, because I want to make sure everybody's got this down. Do you all know which numbers have primitive roots and which ones don't? You remember the theorem, 8.10? This one should be on your flashcards under your pillow at night. Osmosis, it will sink in, right? So the numbers that have primitive roots, so n has primitive roots if and only if. All right, so the choices are 2, 4. Okay, you always just list those off first. And then what else? P to any power, so including p itself, but let's just put all the powers of the prime together. And what else? Great. Okay, so any number that is of any one of these forms has primitive roots, and then if I ask you how many it has, you can do phi of the number. Okay, so p to the k would be one of those cases. Right. Any other number, so 15, for example, does not have this form because 15 is the product of 2 different odd primes. Okay. So anyway, so you want to make sure you know this fact. We didn't actually fully prove this anyway in class. We did part of it. We sort of said that we proved basically the forward part, and then the backwards part was a little trickier. So anyhow, so phi of p to the k is going to tell us how many primitive roots p to the k has, and this is going to be the formula. So how do we do this? Start with phi of p to the k. What would you have me do first to simplify this? Do the inside part. Okay, good. Does anybody know a formula for phi of a prime power? Basically, you do subtraction. You take all the numbers from 1 to p to the k, and you subtract the ones that are not relatively prime to p, which would be anything that's not a multiple of p, and there'd be that many of them. So you subtract that out. Okay. So we get that. That's not what we're trying to prove though. So what would I maybe do next with this expression? Does it respect subtraction?
Oh.
Definitely. Okay, go do that. Okay, so, but working inside the parentheses, I can do what? Rewrite it how?
Take out p to the k minus 1.
Yeah, take out the p to the k minus 1, that leaves you with p minus 1, right? Okay, so just factoring there. Okay, anything I can do, what do you want me to do with what I have now? Why can I break these apart?
P minus 1.
Okay, so p to the k is relatively prime to p minus 1. Is that clear? Well, the only numbers that are going to divide p to the k will be powers of p, right? Oh, I'm sorry. That's supposed to be... Now I just occasionally make sure everybody's paying attention. So, yeah, that should have been k minus 1 power. So we have that times that. So how do I know that... so p to the k minus 1, its only divisors are going to be powers of p. If you look at its prime factorization, it's just p a bunch of times. And that is not going to be a prime factor of p minus 1 because all of the prime factors of p minus 1 have to be less than p for sure. Right? So this step here is by theorem 7.2. That's a really important theorem. I did that one quite a while ago now, and it was we drew this big chart on, I think it was over on this board to show an example of 30. I think I did 10 times 3. Review that. That's one of your theorems that I'm wanting you guys to know for the test. All right, so we get this part, and I still don't know what to do. Can anybody help me yet? What can I do next?
Now you can take p of k to k minus 1.
This one, right? I could take phi of, this is still a prime power, so I could rewrite it as p to the k minus 1 minus p to the k minus 2. And I'll just leave the last part by itself for a moment again. All right. And now what?
Well, p to the k minus 2.
Good. I'll factor out a p to the k minus 2, and that leaves me with p minus 1, and then times phi of p minus 1.
P minus 1 is equivalent to p of p.
So yeah, p minus 1, well, you're kind of looking at what you're trying to prove here, right? This is p squared minus p is really just p times p minus 1. So you have the phi of p minus 1, so you need to have it multiplied by phi of p. So I would take this p minus 1 and rewrite it as phi of p times phi of p minus 1, right? I'm running out of room here, but this is just purely like a algebraic proof. It's not like a lot of depth here. You don't have to write a lot. And then the very last step then is going to be, I'll just come up here, p to the k minus 2. I can put these two together, right? Again, two consecutive numbers are definitely going to be relatively prime, so I'm allowed to multiply them together, and I'll just end up with p squared minus p. Make some sense? Okay, so that's just fiddling around. I just wanted to remind people of the formula for p of a prime power, and the fact that relatively prime numbers respect that multiplication. So that was the purpose of that. Any questions on it? Let's do another example about the Euler phi function that's a little more, interesting in some ways. It's not like I would ever expect anybody to memorize this, by the way. You have to understand, like, I'm not putting these things up here as like, oh, there's something else you need to remember or memorize. These are examples of things that you can derive on the fly, right? The question really isn't, do you have these facts memorized? The question is, do you have the tools and know when to apply which tool to be able to push these proofs through? That's really, at the end of the day, at the end of the semester, what I want for all of you. I want you all to be able to use the tools that we've learned to solve a new problem. So I hope that's the way you're looking at this. I hope you're not looking at it as, oh, there's And another thing I gotta put on a note card and memorize it, right? You could all derive this, right? If hard pressed, you could all derive this on the spot. Not because you've memorized it, but just because you know the basics of how the Euler phi function works, right? Okay, good. Okay, so I wanted to do another one that's kind of along these lines. Okay, so number 5. Let P be prime such that 2P plus 1 is not prime. What is the smallest prime for which that's true?
Seven.
Yeah, 7 is the right answer. So this is just so you know, P is at least 7. 2, 3, and 5 all have the property that when you multiply by 2 and add 1, you do get prime. But 2 times 7 plus 1 is 15, which is not prime. So let's suppose you have that. Okay, then here's the question. Prove that there is no integer n, no natural number n, with phi of n equal to 2 times p. So you can never get 2p out of this. Again, this isn't something that you would like memorize the proof of, but this would hopefully fall into a family of problems that's similar to something you've seen before, so that you know the tools. You've seen these tools being used, how to prove something like this. So in other words, prove that you can never get 2p as an answer, assuming that 2p plus 1 is not prime. If 2p plus 1 is prime, can I get 2p as an answer? Yeah, because what is phi of any prime? Subtract 1 from it, right? So there you go. So if 2p plus 1 was prime, this would be not true at all, right? We have a counterexample. Okay, so any ideas what we're going to do here? How would we try and prove something like this? Spread the wealth here. Prove that something doesn't exist. Yeah, by contradiction, let's suppose it does exist. That's what I would do. Okay, so by way of contradiction, suppose that phi of n is equal to 2p. Okay, let's do that. All right, any suggestions what we should do next? I have to cut you guys some slack, don't I? Because the test isn't for 4 days, so you probably haven't reviewed all the group works and the examples that are kind of like this before. But does anybody remember? Because we did one like this in the group work. Yeah. Correct. You take the number n and you imagine prime factorizing it. Okay, so that's exactly right. And we're talking about the number n. So you want to take the number n and write down a prime factorization of it. So let me write it as, I don't know, p1 to the, what did I use here? K1 times p2 to the k2, dot, 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 up to, let's say, pr to the kr, as its prime factorization. That's basically the fundamental theorem of arithmetic that says we can always factor a number into a prime factorization. Yes?
And here, I mean, even though we're supposing p is greater than or equal to 7 here, it doesn't matter what p1, p2, pr, they can be 2, 3, and 5?
Yeah.
Okay.
Yeah, exactly. So I'll just say where the pi's are distinct primes. Yeah. at this point, we don't want to, we're going to start saying things about what those primes are in a minute, but for now, they're just distinct primes, and let's just say that each ki is at least 1, because if there was some exponent that was 0, you wouldn't write it down, because that term wouldn't even appear there. So just assume that you have a bunch of distinct primes raised to at least the first power. Okay, this is a good time to review phi of n when I have the prime factorization of n. Does anybody know the formula for that? Go ahead, Bora. Phi of n equals?
N times 1 minus 1 over P1.
1 minus 1 over P1.
1 minus 1 over P2.
Good, right. So it's just the product of all of these guys, right? If you remember that, that's, I forget, it's theorem 7.3, I want to say, 7.3 or 7.4, something like that, back in chapter 7. So there's the expression, right? There's the expression. And so this is supposedly, this somehow is going to be equal to 2p. Going to equal to 2p. So n is here, is multiplied by all these fractions, kind of shrinks it down so that it's only equal to 2p. But remember that p is at least 7. P is at least 7, right? Okay, can anybody see how we can work with that? Or want to rewrite it, or, I don't know, any ideas? What we could say?
Just rewrite all the parentheses.
Yeah, or you want to rewrite all the parentheses? Okay, so how would we do that? N times
P1 minus 1 over P1.
P1 minus 1 over P1, okay.
P2 minus 1 over P2.
P2 minus 1 over P2, okay. This is just rewriting it, okay? Just rewriting it. And then PR minus 1 over PR, all of that still equal to 2P, right? Still equals 2P. And now, of course, you have this n, which is written in this form, and now you have some denominators that are going to cancel one of those primes from each of those terms. So if I take the n and divide it by one copy of each of its prime powers, what will I end up with? I'll end up, because I want to get rid of fractions. Guys, this is number theory. We don't want fractions. Okay, so we want to deal with whole numbers here. So right, this has fractions in it, that's not good. This still has fractions in it, that's still not good. But what we can do is we can take n and divide it by the product of the primes, and that will leave me with, what, P1 to the K1 minus 1, P2 to the K2 minus 1, etc., up to PR to the KR minus 1, and then P1 minus 1, P2 minus 1, etc., up to PR minus 1, all of that equal to 2 times P, and remember, we're trying to get a contradiction. Yeah, we're trying to get a contradiction here. Okay. You have an idea?
Do you want someone else to?
I don't care. Does anybody, well, okay, sure. Does somebody have an idea what we want to do next?
You could try to say that P must divide one of those two.
Is that what you were going to say? No.
I was gonna
I don't know. So P divides, yeah, that's true. So P, of course, divides 2P, therefore it divides this whole product. So it has to divide something here.
One of them.
Right. Of course, it could be one of these primes, or it could be these composite numbers, which have lots of prime factorizations in them too. So that's a little tricky. Yeah.
I was gonna rewrite them where you put the P1K minus 1 and the P1 minus 1 together, and you put like the P2 respectively, and then you can then rewrite it as like P of PK1 times P of PK2, that kind of stuff.
So you could put all the P1s together, basically.
Yeah.
Okay, so we could do that. So this would be P1 to the K1 minus 1 times P1 minus 1. And then the next term would be P2, K2 minus 1 times P2 minus 1. All all the way along, PR to the KR minus 1. So we're just reorganizing the terms, really, what we're doing here.
And then.
Okay. Yeah, all right.
And then now those terms, all the P1 terms, that equals P of P1 to K1. And then all the P2, that equals to P of P2 to P2.
Yeah.
So then,
No, ultimately, it's gonna equal phi of n, right?
yeah.
So I don't really wanna go back to that. This is where I started from, and I've broken it down to this point. I don't wanna go back to, we don't wanna use phi at this point. Can any of these primes be, bigger than 3 on the left side? Let me ask you this question. On the right-hand side, how many factors of 2 are there on the right-hand side of the equation? Only 1, because look, P is at least 7, so it's an odd prime. So the number of factors of 2 here is only 1, right? If I had a prime like a 5 or a 7 or a 11 or a 13, if that was one of my primes, what would happen on the left-hand side? Yeah, so if P1 was 5, this would already be 4, right? If it was 7, then I guess this would be 6. That's not a contradiction, is it?
No, but then you have one more prime.
Yeah, so I could have one of these primes, though, equal to...
Can we just consider the fact that there are many different primes on the left side, and we're only declaring that there's only one prime on the right side?
Well, there's 2 primes here.
At most 2 primes.
Yeah.
So if R is going to be greater than 3 or greater, then we're saying that there's going to be 3 different types of primes on the left side against 2 types of primes on the right side.
So there's
And therefore declaring that one of those primes has to be composite, which is a contradiction.
Or that there's two different ways to write the same number, 2 different prime factors.
Let me think about it a little bit. I oversimplified this because I like what you're saying. The only thing is that, so if you had several primes, but the exponent was a 1, so if the k, let's say that k1 was 1, let's say all these k's were equal to 1, right? Then the exponent now is a 0 exponent, right? And I guess you have these parts as well. So you have a lot of stuff here.
But the parentheses are all even.
The parentheses are all even.
Which means it's 2
Yeah.
times something. And can I argue then that P1 minus 1 is different from P2 minus 1? So you're not...
Yeah,
at least
the
some
primes
form
are
of
distinct. These are definitely distinct primes.
And regardless of that then,
Okay.
you're still in the same argument that you have more distinct primes on one side than on the other. Which means
Yeah.
that... you
Yeah,
can
I
either
think
system
I think it's definitely pretty simple to get a contradiction. It's just a little bit of
wording.
I need to write it down carefully. Yeah, basically, yeah.
You're just trying to show that there's more factors of 2 on the left than on the right, right?
That would do it. That would be sufficient.
You're saying that each of those P1, P2 are all primes,
Mhm.
which they're odd primes? Can
Well,
you
no,
say-
we didn't say that, did we?
Okay, so they could,
The,
but they're
the,
distinct.
right, there could, so